because we've already done capacitors in series and parallel. So it's pretty similar. So I can kind of glide over a little bit faster. Resistors in series and parallel. So just like capacitors in series, resistors in series is going to be two resistors that are end-to-end, and they have the same current going through them. And if the battery has an internal resistance also, so all three resistors will be in series. Rint, R1, and R2, right? But for now, we're going to assume the battery has Rint is 0. So assume the battery is a new battery, and for a while, ignore the internal resistance of the battery now. So how will these resistors add up? Well, their voltages will add up. That's similar to how capacitors, same with capacitors, right? The voltages of two capacitors in series add up to give you the voltage of the battery. Well, same here. V tot is V1 plus V2. And then V tot is I tot, R tot. Okay. And then the I1, I tot, I1, I2 is the same. So they cancel. So you end up with R tot is R1 plus R2. So this is similar to how I proved the addition of capacitors, but the capacitors, it ended up being 1 over C tot. Okay, now in parallel, this is parallel here. So the current will come, I, split up into two cases, I1, I2, okay? And then together they will join here. So in this case, their voltage will be the same. The voltage of the battery is the same as the voltage of each resistor, but the currents add up. So I is equal to I1 plus I2. The total current, I can say I tot if I want. The total current is the I1 plus I2. And then I can use the fact that the total current is V tot over R tot. And then the V tot, V1, V2 cancel. And you get 1 over R tot is 1 over R1 plus 1 over R2. It's interesting, when I first learned about this, you know, that resistors add in series R1 plus R2, but capacitors add the opposite way of resistors. And then the parallel, resistors in parallel add up this way, and capacitors in parallel add up the other way. So they're reverse of each other, right? I remember I asked myself, why is it that they add up differently? And I try to justify it to myself. Why do they add up differently? And then I thought and thought and thought about it, and then I realized it's somewhat arbitrary how they add up. It's based on our definition of capacitance and our definition of resistance. Okay? Remember, how was the capacitance defined? In chapter 26. It's Q over delta V. Or let's just write it as Q over V for now, okay? And then how is the resistance defined in terms of Ohm's law? V equals IR, right? It's not really a law. It's sort of that sort of can be taken as a one of the working definitions of resistor, right? So V equals IR, right? So now if I want to define R, define it as V over I. Now do you see how they're defined opposite to each other? R is the measure of how much voltage difference is across a battery or across a resistor divided by how much current is flowing through there. And C is how much charge you have on the battery divided by how much voltage is across that capacitor. Okay? I mean, I think I said battery. I meant capacitor. Now, why are they defined opposite? Why couldn't we just say C is V over Q and make life easy for us? We could, right? They could have defined C as V over Q, and then what would have been the capacitance of a parallel plate capacitor? If C had been defined this way, what would the capacitance of a parallel plate capacitor be? Well, what is it now? A is 0 over D, right? Then the capacitance of a parallel capacitor will be D over A is 0, opposite to what it is now. And then the capacitance of a cylindrical capacitor would be reverse. Capacitance of a spherical capacitor would be reverse. And then when you want to know how capacitors add in parallel and series, then it would have been exactly the same. And life would have been easy. So they wanted to make it, the reason they defined it this way is they wanted to make it different than the resistor and make life a little harder for us. Right? That's all, just that. But then, you know what, another thing, capacitors would it be big then? Right? You know how now most modern capacitors, they are, when you buy it, it says microfarad on it. Nanofarad, picofarad, microfarad, maybe millifarad. But if we had defined it opposite, what would it be? It'll be kilofarad, megafarad, gigafarad, or terafarad. That's the only thing, the labels would change. And their function wouldn't change. They would still remain capacitors, right? So in other words, we could have defined C as V over Q, and life would have gone on the same. Capacitors would still be found in circuits. The only labels would change, you know. And capacitors in series would then add like resistors in series. So let me go back to my original question then. Why the heck did they define it opposite? There must be something more logical about defining it as Q over V versus defining it just like a resistor. So here's how I do in order to justify the definition. I say, what is the definition of a good capacitor? Okay, I try to think to myself, what is the definition of a good capacitor? Well, it's probably something that I don't need to put a lot of voltage to, and I can still store a lot of charge in it, right? I don't need to put a lot of voltage across it, but it will still store a lot of charge. So a good capacitor is something where the V is small, but the Q is still big, right? So based on that, which of these two would give you the good answer? If V is small and Q is still big, you get a high C. Okay? If V is small and Q is still big, mathematically you would get a low C. Right? If V is small, Q big. That doesn't make sense. If I only need to put a little voltage and I can store a lot of charge on it, how could it be a low capacitor? Do you see? So by the very definition of what you think of as a good capacitor, you're forced to define C as Q over V, not V over Q.